Okay, let's unpack this. Welcome to the deep dive. Today we're tackling a topic that, frankly, messes with people's heads a bit. Concurrency and synchronization primitives in operating systems.
Yeah, it's definitely one of those areas.
You handed us this stack of source material articles, research papers, looks like some course notes maybe, and our mission, as always, is to dive deep, pull out the most important knowledge, the key insights, and basically give you the shortcut to being really well informed on this challenging subject.
It really is one of those areas that forces you to think differently. Concurrent programming, where different parts of your code are potentially running at the same time, it just introduces some fundamental complexities.
Right.
So we're going to use your sources here to guide us through why we even bother with concurrency in the first place, expose the core problems it inevitably creates, and then explore the foundational tools that operating systems and libraries give us to manage that chaos.
Think of this as your guided tour through the guts of multi-threaded programming. We'll start with the absolute basics, what threads are, how they're different from processes. Then, boom, we immediately hit the wall. Race conditions.
It's a classic problem.
Exactly. Once we really understand that critical problem, we'll spend the bulk of our time exploring the big three solutions. Locks, condition variables, and semaphores.
The workhorses.
Yeah. And just when you think you've got it, we'll pivot and look at a completely different way of handling concurrency, this event-based programming idea.
It's a crucial area, It underpins everything from responsive user interfaces to, high-performance web servers, and, of course, the operating system kernel itself. So this deep dive, it's built specifically from the material you gave us, aiming to give you the clearest possible picture of these mechanisms.
All right, let's jump right in then. Why even bother with concurrency? What's the fundamental motivation, according to these sources?
Okay, so the sources lay out two primary drivers. The first, and maybe the most obvious one today, is simply hardware utilization. You've got multi-core processors everywhere now.
Right, in everything.
Yeah, so concurrency is absolutely essential to make your program run faster by actually using those cores, dividing work across different CPUs simultaneously. If your program isn't concurrent, it's probably just sitting on one core, leaving the others totally idle.
So if I want my program to actually use that fancy multi-core chip I paid for, I need concurrency. Simple as that.
Pretty much, yeah. The second reason, which goes back a bit further in computing history, is handling I/O efficiently. Programs often have to wait for slow stuff, reading from a disk, sending data over a network, waiting for you to type something.
Little slow parts.
Exactly. Instead of the entire program just grinding to a halt while it waits, you can use threads. So while one thread is blocked on that slow I/O, the OS scheduler can just switch to another thread within the same program that is ready to compute or do something useful.
Ah, okay, so it's about overlapping that waiting time with doing actual work. That makes a lot of sense. Now, the sources talk about both threads and processes. What's the key difference in this context that kind of pushes us towards threads for a lot of these concurrent tasks?
The fundamental difference, the one highlighted here, is how they share data. Threads within the same process. They share the same address space.
Okay.
They live in the same virtual memory world, which makes it super easy to access and modify shared data structures directly. Just access the variable.
Right.
Multiple processes, though, they have completely separate address spaces, totally different memory worlds. While you can share data between them using things like shared memory segments or message passing, it's significantly more complex than just having two threads look at the same variable in memory.
So that easier data sharing is a major plus for threads when you're building, say, one application where different parts need to work together closely. And conceptually, a single-threaded process is one stack, but multi-threaded is multiple stacks, one per thread, but they're all inside the same shared heap and code space.
And precisely. That's a great way to picture it. Each thread needs its own call stack for its function calls, its local variables, return addresses, all that stuff, independent of the others. But they all see the same global variables and the same heap memory.
Okay, it makes sense. So how do you actually get these threads up and running? The sources here lean heavily on the POC X-Threads API, or threads.
Yeah, that's pretty much the standard for C and C++ on Linux, Mac OS, lots of systems. The core function for creating a new thread is thread create. It's actually pretty straightforward when you break it down. You give it a place to store the new thread's ID, which is a threat type variable. Then optional attributes, usually just NULL for the defaults. Then the name of the function, the new thread, should start running. And finally, a single argument, a void A, to pass to that start function.
Like that simple example in the source, the one that prints A or B, you just pass the character A or B as that void argument?
Exactly that. You cast the character to void and pass it. You start multiple threads. Maybe they run the same function but get different arguments, and then the OS scheduler just takes over, deciding who runs when and for how long. You can get all sorts of unpredictable interleavings of A's and B's.
Okay, so that gets them started. How do you, wait for one of those threads to finish its job if the main thread needs a result or something?
That's thread join. You pass it the thread identifier of the thread you want to wait for, and your calling thread just stops. It blocks until that target thread finishes its execution.
Does it get anything back?
Yeah, you can optionally get the target thread's return value. There's an argument to thread join where you can pass a pointer, and the system will put the return value there. Or you can pass NULL if you don't care.
Speaking of arguments and return values, the sources get into the mechanics here. They show how you might pass, complex data using structs or simpler types just by casting.
Oh, yes, exactly. Packing multiple data points into a struct and passing a pointer to that struct is super common if your thread's start routine needs more than just one simple argument. And for return values, yeah, you typically return a pointer to something, often something allocated on the heap.
But there's a huge warning sign in the sources about what not to return a pointer to.
Oh, yeah. This is absolutely critical, and it's a super common source of really subtle, nasty bugs. Never return a pointer to memory allocated on the thread's own stack.
Because the stack disappears.
Exactly. But remember how each thread gets its own stack? When that thread's start function returns, when the thread finishes, its stack space is just gone. Poof! Reclaimed by the system. So if you return a pointer to a local variable that lived on that stack, that pointer is now pointing to garbage, or maybe memory that's being reused for something else entirely, trying to access it later from another thread. That leads to undefined behavior, what the sources nicely call all sorts of bad results.
Yeah, bad results sounds like an understatement. Seg faults, weird data corruption.
All the above. So the rule is, any data that needs to be shared between threads or needs to live longer than the thread that created it absolutely must live somewhere else, usually the heap.
So dynamic allocation with malloc or new is the way to go for shared or returned data.
That's the standard approach, yes. Allocate on the heap, pass pointers around, and make sure someone cleans it up later.
Got it. And the practical stuff, compiling this code.
Pretty simple usually. You need to include the thread.h header file for all the declarations, and then when you compile, you need to link against the threads library. With GCC or Clang, that's usually just adding the paretic thread flag on the command line.
Okay.
The API itself, thread create, thread join, thread mutex lock, there aren't that many functions. The core API is small, which is kind of deceiving because using it correctly without shooting yourself in the foot, that's where the real difficulty lies.
And that difficulty comes up immediately that we start talking about shared data, right?
Yeah.
We have these multiple threads. They can all see and modify the same memory. What happens when they try to touch the same piece of shared data, the exact same time?
This is it. This is the absolute core problem. Concurrent access to shared mutable state. That's where things go sideways. The sources use that classic, seemingly totally innocent example, incrementing a shared counter variable. Just counter, +1.
Yeah, that looks like one single atomic step. Add one to the counter. Done.
That's the illusion. At the hardware level, even something simple like counter +1 is typically broken down into several distinct machine instructions. Usually something like 1, load the current value of counter from memory into a CPU register. 2, increment the value in that register. 3, store the new value back from the register to the counter location in memory.
Okay, right. Load, increment, store. 3 steps. Now, introduce multiple threads doing that sequence.
Exactly. Let's walk through it. Imagine 2 threads, thread 1 and thread 2. Counter starts at 0.
Executes the load instruction, reads 0 into its private CPU register.
Okay, got 0.
Now the scheduler interrupts thread 1, crucial point. Switches to thread 2.
Executes its load instruction. It also reads the value of counter from memory, which is still 0. So thread 2 also has 0 in its private register.
Both think the counter is interrupt?
Yep. Thread 2 continues, executes increment. Its register now holds 1.
Executes store. Writes 1 back to the counter variable in memory. Counter is now 1.
Okay, counter is 1.
Now, the scheduler switches back to thread 1. Thread 1 resumes where it left off. It already did the load.
Right. It still has 0 in its register from way back when.
Exactly. So thread 1 executes increment. Its register goes from 0 to 1.
Executes store. Writes the value from its register, which is 1, back to the counter in memory. Counter was already 1, now it's still 1.
Oh, wow. Okay. So 2 threads both performed an increment operation. They both ran their load increment store sequence. But the final result is 1, not 2. That's just wrong.
Completely wrong. And that is a race condition. The final outcome is non-deterministic. It depends entirely on the precise, unpredictable timing and interleaving of how the scheduler runs the threads. The threads are racing to access and modify that shared counter, and the result depends on who finishes their sequence of operations when, especially that final store. It's unprotected access.
So a race condition is basically when the correctness of your program depends on sheer luck regarding thread timing, which you absolutely cannot control.
That's a perfect way to put it.
Yeah.
And to avoid this disaster, we need to identify these dangerous parts of our code. We call them critical sections.
Right.
A critical section is any piece of code that accesses shared resources, like those 3 instructions for counter, counter plus 1, and must not be executed by more than one thread at the same time. If multiple threads enter, you get chaos.
And the property we need to enforce, the guarantee that only one thread gets in, is mutual exclusion.
Correct. Mutual exclusion is the goal. We need a mechanism to ensure that only one thread is executing inside that critical section at any given moment. This isn't a new problem, by the way. The sources mentioned this fundamental concept was clearly articulated way back in the early days of concurrent programming by pioneers like Ismager Dijkstra.
Okay, so just writing the code like counter plus 1 isn't enough. We need something extra, something outside that simple code to make sure only one thread can do that load increment store sequence at a time. We need synchronization tools.
Exactly. You can't reliably build these synchronization tools using just standard loads and stores on regular variables. We saw how that fails. You need help, typically from the hardware and the operating system, to provide the special atomic operations required to build reliable synchronization primitives.
Which brings us neatly to the most common tool for enforcing this mutual exclusion. Locks, or mutexes.
Yes, locks, or mutexes, short for mutual exclusion. They're the absolute workhorse for this. The idea is simple. You wrap your critical section code with lock and unlock calls. A thread calls lock before entering the critical section, and it calls unlock immediately after exiting.
Like putting up a velvet rope in a one-person-only sign around that critical section code.
That's a pretty good mental model, yeah. If a thread calls lock and the lock is currently free, no one else is inside, the thread acquires the lock, gets past the rope, and continues into the critical section. But if it calls lock and another thread already holds the lock, someone's already inside, the calling thread blocks, it just stops executing right there and has to wait. It gets put in a queue, essentially.
Waits its turn.
Waits its turn. When the thread that currently holds the lock eventually calls unlock, it releases the lock, takes down the rope, and the system then wakes up one of the waiting threads, if any, lets it acquire the lock, and proceed into the critical section.
Got it. And the sources really hammer home the importance of initializing these locks properly.
Oh, absolutely critical. Using an uninitialized lock leads to completely undefined and usually disastrous behavior. You must initialize them before you use them for the first time. You can do it statically at compile time using pthread mutex initializer, or dynamically at runtime with thread mutex in it. It's a tiny step, but so easy to forget, and the consequences are huge.
Right, like forgetting to put the velvet rope up in the first place.
Yeah.
And always checking return codes from the lock functions.
Yes. Good practice for pretty much any system call, but vital here. If thread mutex lock returns an error, it means you didn't actually acquire the lock. If you just ignore that error and proceed into the critical section anyway, well, you're right back to having a race condition because you aren't actually protected.
Okay, so we need locks. And we need them because simple attempts, like using just a plain flag variable, non-skulls1, don't work. Why exactly do those simple flag attempts fail? We touched on it with the counter, but let's nail it down.
It comes back to that lack of atomicity. The check and the set flag 1 are 2 separate operations. A malicious scheduler or just unlucky timing can interrupt a thread right between those 2 steps. So thread A checks the flag, sees it's 0, meaning free. It decides, okay, I'm going in. But before it can execute flag use 1 to claim it, zap, it gets interrupted. Scheduler runs thread B. Thread B also checks the flag. It's still 0 because thread A never got to set it, so thread B also thinks, great, it's free, and decides to go in. Now you potentially have both thread A and thread B about to enter the critical section because neither one's check then set sequence completed without interruption.
Right, because neither the check nor the set individually prevents the other thread from observing the state in between, that critical gap.
Precisely. You need a single operation that performs both the check and the set, or something equivalent, as one uninterruptible atomic unit, and that's where the hardware has to step in.
Hardware support. Special atomic instructions, like test and set.
Right.
The hardware provides special instructions that the CPU guarantees will execute atomically, no interruptions allowed mid-operation. Test and set address is a classic example mentioned in the sources. It does three things atomically. Reads the current value at the memory address, unconditionally sets that memory location to 1, and then returns the original value it read.
How do you build a lock with that?
You can build a basic spin lock. You have a lock variable, say initialized to 0, meaning free. To acquire the lock, you repeatedly call test and set on the lock variable's address in a loop. If test and set returns 0, it means the lock was free, its original value was 0, and you just successfully set it to 1, acquired it. You break the loop and enter the critical section. If test and set returns 1, it means the lock was already held. Its original value was 1. So you just stay in the loop spinning, calling test and set again and again until it eventually returns 0.
Okay, spinning until you get it.
Right.
And compare and swap, that's another one mentioned. Another very common and powerful one, compare and swap address expected value new value. This one is a bit more sophisticated. Atomically, it does this. Checks if the value currently at address is equal to expected value. If and only if it is equal, then it updates the value at address to new value. Regardless of whether it updated or not, it returns the original value that was at address before the operation started.
How's that used for locking?
You can try to acquire a lock, again, let's say 0 means free, 1 means held, by calling compare and swap lock address 0, 1, you're saying. If the lock is currently 0, the expected value, atomically set it to 1, the new value. If the value returned by compare and swap is 0, it means it succeeded the lock was 0, and you just set it to 1. You got the lock. If it returns 1, it means the lock was already 1 when you called, so the swap didn't happen, and you didn't get the lock. You'd spin and try again.
Got it. And fetch an add.
Fetch an address. This one atomically reads the value at address, adds 1 to it or some other value, stores the new incremented value back, and returns the original value before the increment.
How is that useful for locks?
The sources show a really neat application, building a ticket lock. It provides more fairness than a simple spin lock where threads might barge in. With a ticket lock, you have 2 shared variables, ticket and turn, both starting at 0. To acquire the lock, a thread calls fetch and add on the ticket variable. This atomically gives the thread the next available ticket number, say thread A gets 0, thread B gets 1, etc., and increments the ticket counter. Then the thread spins, but not on the lock itself, but waiting for the global turn variable to become equal to its ticket number. When the thread currently holding the lock is done, it simply increments the turn variable. This signals that the next ticket holder, the thread with ticket first turn, can now proceed.
Like taking a number at the deli counter. Ensures first come, first served.
Exactly. It provides FIFO, first in, first out ordering, which can be much fairer than simple spin locks where a thread might spin for ages while others get the lock repeatedly.
These atomic instructions are clearly powerful building blocks, but that spinning, just looping and checking, that sounds incredibly wasteful, especially if the lock is held for a long time.
Oh, it absolutely is. Spin locks, built purely on these atomic hardware instructions without any OS help, can be terribly inefficient. Think about it. On a single processor system, if thread A holds the lock and gets interrupted, any other thread, thread B, trying to acquire the lock will just spin uselessly, burning 100% CPU, because thread A can't run to release the lock while thread B is spinning. Even on multiprocessors, if lock contention is high or locks are held for non-trivial amounts of time, all those spinning threads are just wasting valuable CPU cycles, doing absolutely nothing productive. It's called busy waiting for a reason.
So to avoid that pointless busy waiting, locks need more. They need help from the operating system.
Exactly. To make locks efficient, especially when contention is high or when locks might be held for a while, the OS needs to get involved. The idea is simple. When a thread tries to acquire a lock that's already held, instead of just letting it spin wildly, the OS can intervene. The OS can put that thread into a sleeping or blocked state. The sources mention underlying primitives like park or block. The OS then takes that thread off the run queue and schedules a different, useful thread to run instead.
So the CPU doesn't get wasted on spinning.
Right. Then, when the thread that was holding the lock finally calls unlock, that unlock operation does more than just change the lock state. It also notifies the OS maybe via a call like unpark or wake saying, hey, the lock is free now. The OS can then look at the queue of threads that were sleeping, waiting for this specific lock, pick one, wake it up, put it back on the run queue, and eventually it will get scheduled, acquire the lock, and proceed. The OS manages the waiting queue and the sleep-wake mechanism.
So OS support is absolutely key for locks to be efficient and fair, beyond just simple, busy waiting on hardware atomics.
Precisely. And in practice, as the sources hint, many real-world lock implementations often use hybrid approaches. They might spin for a very short time, first a few cycles or microseconds, hoping the lock will be released really quickly. It's optimistic. But if the lock isn't free after that brief spin, then they yield to the OS and go to sleep to avoid wasting CPU. That's often called a two-phase lock.
Okay, that makes sense. So locks handle the critical section protection, the mutual exclusion. But what if a thread needs to wait for something more specific than just is the lock available? What if it needs to wait until some condition about the shared data protected by the lock becomes true? Like, waiting for a shared queue to actually have an item in it before trying to remove one, or waiting for another thread to signal, hey, I finished processing that data you gave me.
That's exactly the problem that condition variables, or CVs, are designed to solve. You could try to implement this with just a lock and some shared flag variable that you check in a loop inside the critical section, like while queue's empty, unlock mutex, maybe sleep, lock mutex.
Tell me.
But as the sources make crystal clear, that kind of spinning or manual sleeping polling is super inefficient, and it's incredibly difficult to get right without introducing subtle race conditions. Research has shown time and again that these kinds of ad hoc flag-based synchronizations in concurrent code are notoriously buggy.
Okay, so spinning on a condition inside a lock is bad. Condition variables are the better way. How do they work? Are they like queues for threads waiting for specific conditions?
That's a good way to think about it. They're explicit queues that threads can associate with some shared state, which is itself protected by a mutex. A thread can call wait on a condition variable and atomically go to sleep joining that queue. It will stay asleep until some other thread explicitly changes the state and then calls signal on the same condition variable, indicating that the condition the first thread was waiting for might now be true. The standard threads routines are thread conwait and thread consignal.
Got it. Now, thread conwait has a really interesting signature. The sources point this out. It takes both a condition variable and a mutex as arguments. Why does it need the mutex too? That seems weird at first glance.
Yeah, it does seem weird, but it's absolutely fundamental and often trips people up. Here's the magic of thread conwait. When a thread calls it, it must atomically perform two actions. One, it releases the mutex that was passed into it. Two, it puts the calling thread to sleep on the queue associated with the condition variable.
Whoa, okay. Atomically release the mutex and go to sleep. Why on earth does it release the mutex? Isn't the whole point to hold the mutex while checking shared state?
Think about the scenario. Your thread holds the mutex because it just checked the shared state and found the condition it needs isn't true. For example, the queue is empty. It now needs to wait. If it kept holding the mutex while it went to sleep waiting, how could any other thread ever get in to change the state? The other thread, the producer in this case, needs to acquire that same mutex to add an item to the queue and make the condition true. If the waiting thread held the mutex, the producer would block forever trying to acquire it. Deadlock. So, thread conwait must release the mutex as it goes to sleep to allow other threads to acquire the lock, modify the shared state, and eventually signal.
Okay, that makes perfect sense now. Releasing the mutex is crucial to allow progress. So it releases the mutex, goes to sleep. What happens when it eventually gets woken up by a signal?
This is the other critical part of the magic. When thread conwait is woken up, because another thread called thread consignal or thread con broadcast on the same CV, before the thread conwait function actually returns control to your code, it automatically reacquires the mutex for you.
It grabs the lock back.
Yes, atomically as part of the wake-up process. So when your call to thread conwait finally returns, you know two things. One, someone signaled you, possibly because the condition might be true. And two, you are once again holding the mutex. This ensures that when your thread continues executing after the wait, it holds the necessary lock and can safely re-examine the shared data to verify if the condition that woke it up is actually truly met now.
And that leads directly into the famous absolutely critical while loop requirement when you're waiting on a condition. The sources are really adamant about this. Always check your condition inside a while loop, not an if, like while condition to be as a mutex.
Yeah.
Great. Why is the while so essential? Why isn't if condition is not met, wait, good enough?
This is probably the single most common mistake people make with condition variables. The reason you must use a while loop comes down to how most systems implement signals using what are called mesa semantics.
Mesa semantics.
Yeah. It basically means that a signal on a condition variable is treated as just a hint that the condition might be true now, not a guarantee that it is true and will stay true until you run. There are several reasons why you can't rely on it being true when you wake up. One, the lost wake-up problem, if you used if. Imagine thread A checks the condition, for example, is D empty, finds it true, so it decides it needs to wait. It's about to call thread con wait. But just then, scheduler switches to thread B. Thread B adds an item to the queue, making it not empty, and calls thread can signal. Since thread A isn't actually waiting yet, the signal doesn't wake anyone up. It's lost. Now thread A runs again, enters thread con wait because it only checked with an if, and goes to sleep, possibly forever, even though the queue is no longer empty. 2. State change after wake up. Thread B signals, waking up thread A. But before thread A can actually run and reacquire the mutex, the scheduler runs thread C. Thread C acquires the mutex, removes the item thread B just added, and releases the mutex. Now thread A finally runs, reacquires the mutex, and returns from wait. If it only used an if, it would incorrectly assume the queue is not empty and proceed, likely crashing when it tries to dequeue from an empty queue. The condition became false again after the signal but before the waiter ran. 3. Spurious wake-ups. This is a weird one, but operating systems are sometimes allowed to wake up a thread waiting on a condition variable even if no signal actually occurred. It's rare but possible due to implementation details or optimizations. Your code has to be robust against waking up for no reason.
Wow. Okay, so the signal is just a suggestion, hey, maybe check again. And the while loop is the mechanism to actually do that check reliably after waking up and reacquiring the lock. Handling all those possibilities of state changing again, or just waking up randomly.
Exactly. When you wake up from thread con wait, you hold the mutex again, you're inside the while loop, so you safely reevaluate the condition on the shared state. If it's still not met, maybe someone else snuck in, or it was a spurious wake up, the loop condition is true, and you just call thread con wait again, releasing the lock and going back to sleep. If the condition is now met, the loop terminates, you proceed still holding the lock, do your work on the shared state, and then eventually release the lock. It's the only robust pattern.
That makes so much sense. The sources use the classic producer-consumer problem to really show this in action with condition variables, right?
Yes, it's the perfect illustration. You've got producer threads adding items to some shared fixed-size buffer, and consumer threads removing items from it. Producers have to wait if the buffer gets full. Consumers have to wait if the buffer becomes empty.
And you definitely need a mutex around the buffer structure itself, right? To protect the actual put and get operations from interfering with each other if multiple producers or consumers run concurrently.
Absolutely. The mutex protects the integrity of the buffer data structure, like its internal count, pointers, the array itself. And then associated with that buffer and that mutex, you typically use 2 condition variables. One CV, let's call it empty CV, for producers to wait on when the buffer is full. Consumers will signal this when they remove an item. 2, another CV, let's call it full CV, for consumers to wait on when the buffer is empty. Producers will signal this when they add an item.
So a producer would lock the mutex, check if the buffer is full using a while loop. If it is, thread confetas an empty store and mutex. Once it wakes up and the buffer isn't full, add the item, then call thread can signal and full CVV to potentially wake a waiting consumer and finally unlock the mutex.
That's the exact pattern. And the consumer does the mirror image dot lock while buffer's empty, wait full, CV and mutex, remove item, signal, and empty CVV, unlock. Using 2 separate CVs helps ensure you only wake up the right kind of thread, a consumer when an item is added, a producer when space becomes available.
Makes sense. And quickly, there's also a thread can broadcast.
Right. Thread can signal typically wakes up only one waiting thread. Thread can broadcast wakes up all threads currently waiting on that specific condition variable.
When would you use that?
It's necessary sometimes. The classic example is maybe a memory allocator where multiple threads might be waiting for different amounts of free memory. When any memory is freed, you might need to wake up all waiting threads because you don't know which one might now be satisfied by the newly available amount. But it's generally less efficient than signal if only one thread can make progress, as it wakes up potentially many threads that will just check the condition, find it false, and go back to sleep. Overuse of broadcast can sometimes indicate a potential logic bug or inefficiency.
Okay, got it. So we've covered locks for pure mutual exclusion, condition variables for waiting on specific state conditions while holding a lock. The sources also introduce a third major primitive, Semaphores, which you mentioned Dijkstra invented.
Yes, semaphores are historically very significant and, in a way, perhaps more fundamental and generalized than locks or CVs. You can actually implement both locks and condition variable-like signaling using semaphores. They're basically just an integer value that you can only interact with using two special atomic operations,
Okay.
sumwait and semppost.
Okay, an integer and two operations. How do those operations work?
So a semaphore holds a non-negative integer value, usually, sumwait, which Dijkstra originally called P for probaran, to test. This operation tries to decrement the semaphore's value. If the value before decrementing was greater than 0, it just decrements it by 1, and the calling thread continues immediately. However, if the value is already 0, the thread cannot decrement, and it blocks, goes to sleep, until the value becomes positive again. Some implementations allow the internal value to go negative to count waiting threads, but the essential behavior is wait if 0, otherwise decrement and proceed. Semppost, which Dijkstra called V for verhogen, to increment. This operation increments the semaphore's value by 1. If there were any threads blocked waiting on this semaphore because its value was 0 when they called semwait, the semppost operation wakes up exactly one of those waiting threads.
And these wait and post operations themselves are atomic.
Yes, the internals of sumwait and semppost guarantee atomicity. The check and decrement or the increment and maybe wake operation happens as an uninterruptible unit.
Okay. How can you use a semaphore to act just like a simple lock, a mutex?
You initialize the semaphore's value to 1. This is often called a binary semaphore. The first thread calls semwait. The value is 1, greater than 0, so it decrements it to 0 and proceeds it has acquired the lock. Any subsequent thread calling semwait finds the value is 0, it blocks, waiting. When the first thread is done with its critical section, it calls semppost. This increments the value from 0 back to 1. If any threads were waiting, one of them is woken up, it will then succeed in its semwait, decrementing back to 0 and proceed. It effectively passes the lock to the next waiting thread.
Neat. A lock built from a counter. And they can also be used for simple signaling or ordering between threads, kind of like we discussed with CVs.
Absolutely. For simple ordering, like having a parent thread wait for a child thread to finish some initialization, you can use a semaphore initialized to 0. The parent thread calls semwait on this semaphore. Since the value is 0, the parent blocks immediately. The child thread does its initialization work. When it's finished, it calls semppost on the same semaphore. This increments the value from 0 to 1 and, crucially, wakes up the parent thread, which was the only one waiting. The parent semwait can now complete, decrementing back to 0, and the parent proceeds, knowing the child is done.
So init to 1 for locking, init to 0 for waiting signaling. Okay, let's go back to the producer-consumer problem again. How does that look using semaphores instead of condition variables?
Right, the semaphore approach for PC is also classic. Instead of condition variables waiting on state, you use semaphores to directly track the counts of available resources. You typically use two semaphores. 1, an empty semaphore initialized to the buffer size, max. This counts the number of empty slots available in the buffer. 2, a full semaphore initialized to 0. This counts the number of filled slots or items available to consume.
Okay, so empty starts high, full starts at 0.
Exactly. A producer wanting to add an item first calls semwait empty. This waits until there's at least one empty slot, value 0, then decrements the count of empty slots. After adding the item to the buffer, it calls semppost in full, incrementing the count of full slots and potentially waking a waiting consumer.
And the consumer does the reverse.
Yeah. A consumer calls semwait full first. This waits until there's at least one item in the buffer, value 0, then decrements the count of full slots. After removing the item, it calls semppost in empty, incrementing the count of empty slots and potentially waking a waiting producer.
Okay, that seems almost simpler, using counts directly. But wait, do you still need a mutex lock around the buffer access itself? Like when the producer actually calls put or the consumer calls get?
Yes. Absolutely, yes. This is another critical point that the sources really emphasize, and a common mistake when first learning semaphores for PC. The semaphores, empty and full, correctly manage the waiting for available slots or items. They ensure a producer doesn't try to put into a full buffer and a consumer doesn't try to get from an empty one. But you could still have multiple producers run concurrently or multiple consumers run concurrently. If two producers both successfully pass semwait and empty and then try to call the put function at the same time, they could create a race condition inside the put function itself while manipulating the buffer's internal pointers or data array.
Ah, right. The semaphores only control entry based on counts, not the access to the shared buffer structure itself.
Precisely. So you still need a binary semaphore initialized to 1, or a mutex lock to protect the critical sections of code where the threads actually interact with the shared buffer data structure, and the correct structure is
Usually semwait, empty, lock mutex, call put, unlock mutex.
semwait in full, lock mutex, call get, unlock mutex, sempost empty. Getting the order of these operations wrong, by the way, like trying to acquire the mutex after waiting on empty or full, is a classic recipe for deadlock. You generally want to grab the mutex before potentially blocking on the condition semaphore.
That locking order detail seems really important and easy to mess up. The dying philosopher's problem is brought up in the sources as another famous example of deadlock potential, often illustrated with semaphores.
It's a great, if slightly contrived, problem for illustrating synchronization challenges. You have philosophers sitting around a table needing 2 forks, the one to their left and the one to their right, to eat. Each fork is a shared resource.
And the naive solution leads to deadlock.
Yeah, the simple intuitive approach is to represent each fork as a binary semaphore, initialized to 1. Each philosopher tries to acquire their left fork, semwait, left fork, and then tries to acquire their right fork, semwait, right fork. The problem is, if all philosophers manage to pick up their left fork simultaneously, then they all block forever waiting for their right fork, which is held by the philosopher to their right, who is also waiting. It's a perfect classic deadlock. Nobody eats.
Starvation, literally.
Yeah.
So what's a simple fix mentioned?
The key is to break that circular dependency in resource acquisition. One common solution, the source mentions, is to have one philosopher, say the last one or an arbitrarily chosen one, pick up their forks in the opposite order. Right fork first, then left fork. This breaks the symmetry and prevents the everyone holding left, waiting for right deadlock scenario from occurring. There are other solutions too, like allowing only N1 philosophers to try and pick up forks at a time.
Okay, so semaphores are definitely versatile locks, signaling, counting resources, but require real care in how you compose them, especially making sure you still use mutexes correctly to protect the actual shared data operations themselves.
Exactly. They are powerful, low-level primitives, but sometimes reasoning about complex waiting conditions can feel a bit less direct compared to using condition variables that are explicitly tied to checking shared state protected by a mutex. Different tools, different styles.
Right. Now, we spent all this time talking about thread-based concurrency and the tools to manage locks, CVs, semaphores. But the sources also present an entirely different paradigm, an alternative approach. Event-based concurrency. You mentioned this earlier, concurrency without using explicit threads.
Yes, exactly. This approach is particularly popular and often very effective in high-performance network servers, graphical user interfaces, places where you're primarily reacting to external inputs. The core idea is built around a single main execution loop, the event loop. This loop basically just sits there waiting for events to happen.
Events like what?
Like a data arriving on a network socket, a user clicking a button, a timer expiring, maybe a signal from the OS. When an event occurs, the event loop figures out which piece of code an event handler function is responsible for dealing with that specific type of event, and it calls that handler.
So instead of the OS scheduler deciding which thread runs when, the application itself, through this event loop, has very explicit control over what code runs and in what order, based on incoming events.
Precisely. There's typically just one main thread of control executing these handlers one after another as events arrive. And this leads to the crucial, absolutely non-negotiable rule of event-based programming. The event handlers must never block.
Never block. Why not?
Because there's only one thread running the event loop and executing handlers. If an event handler decides to perform a blocking operation, say, it calls a standard read function to get data from a file, and the disk is slow, so read, blocks waiting, then the entire event loop grinds to a halt. No other events can be processed, no other handlers can run. The whole server or application just freezes until that blocking call finally returns. It's a showstopper.
Wow, okay. That's a huge constraint. How on earth do they perform I/O, which is often inherently blocking, without blocking the event loop?
They have to rely on non-blocking I/O primitives provided by the operating system. Instead of calling a function like read, which might block if no data is ready, they use system calls like select or poll, or more modern variants like a poll on Linux or a queue on BSD macOS. These functions allow the program to ask the OS something like, hey OS, look at this list of file descriptors, sockets, pipes, etc. I'm interested in. Tell me immediately without waiting which ones currently have data ready to be read or are ready to be written to or have an error.
So they check readiness without blocking.
Exactly. The event loop calls select or poll. The OS checks the status of all the monitor descriptors and returns immediately, indicating which ones are ready. The event loop then iterates through the ready descriptors and calls the appropriate event handlers only for those specific events. If, for example, data are ready on socket X, can write to socket Y. The handlers can then call non-blocking versions of read or write, which are guaranteed not to block because SelectPool already told them data is available or space is ready.
Okay, that makes sense. What's the big selling point of this single-threaded event model then, especially given that strict no-blocking rule?
The primary advantage, especially noticeable on a single CPU core, is the simplicity regarding synchronization. Because only one event handler is actively executing at any given moment, remember they don't block, so they run to completion quickly, you generally don't need locks to protect shared data structures accessed by different handlers.
No locks, really?
Generally, yes. Since only one handler runs at a time, you can't have two handlers trying to modify the same data structure concurrently. This completely eliminates a huge, difficult class of concurrency, bugs, race conditions, deadlocks related to locking that constantly plague multi-threaded programs. That simplicity is a massive win.
Okay, that does sound amazing. No locks, no races. But you mentioned that blocking calls are the big problem. What happens if the event handler really needs to do something that just might block? Like reading a configuration file from disk at startup or querying a database. Those operations often have blocking APIs.
This is the absolute Achilles heel of the pure event-based model. Threaded systems handle this sort of thing gracefully. The thread making the blocking call just blocks, and the OS simply schedules another thread to run. In a pure event loop, as we said, that's a showstopper. So how do they deal with it? One approach is to use asynchronous I/O, AIO, APIs, if the OS provides them. With AIO, you initiate an operation, say AirRead to read from a file. This call returns immediately, without waiting for the read to complete. The OS performs the disk read in the background. Later, when the read is complete, the OS notifies the application, typically by generating another event that the event loop can pick up.
So it turns the blocking operation into a non-blocking request and a future completion event.
Exactly. But the sources note that AIO APIs can often be complex to use correctly, and OS support isn't always universally available or robust for all types of operations. Disk I/O is better supported than some other things.
And the sources also mention hybrid approaches being common.
Yes, very often this is the most practical solution in the real world. You might keep the main event loop running on one thread, handling all the high-volume, non-blocking network I/O efficiently, but then you also create a separate small pool of traditional worker threads. When an event handler needs to perform an operation that might block, like that disk read or database query, instead of calling the blocking function directly, it packages up the request and hands it off to one of the threads in the worker pool. The event handler then immediately returns control to the event loop, keeping it unblocked. The worker thread performs the blocking operation in the background. When it's done, it somehow signals the result back to the event loop, often by queuing a completion event, which can then process the result in a subsequent event handler call.
Okay, so offload the blocking work to a dedicated thread pool. That sounds like a reasonable compromise. Another significant challenge mentioned in the sources for event-based systems is state management. Why is that so tricky compared to threads?
This is perhaps the other major complexity you trade for the lock-free simplicity. Think about how threads work. If you're inside a function in a thread and you call another function, maybe one that blocks, like read, when that function eventually returns, you're right back where you were. All your local variables, the function call stack, the entire context of what you were doing, it's all still there, preserved automatically on the thread stack. You just proceed to the next line of code.
Right, the stack is like automatic state saving for function calls.
Exactly. Now contrast that with the event-based model using asynchronous operations like AIO. When an event handler initiates an asynchronous operation like aread, that handler function usually finishes executing and returns control back to the event loop almost immediately. It doesn't wait. Much later, when the actual disk read completes, the OS generates a notification which triggers a different event handler, or maybe the same handler function but called in a new context, to run. The problem is, how does this new handler know what to do with the data that was just read? What was the original request context? Which client connection was this file read for? All that state information that was implicitly available in the local variables and call stack of the original threaded function call is just gone because the original handler finished long ago.
So you have to manually save all that necessary context somewhere before the first handler finishes and then retrieve it somehow when the completion handler runs later. The sources call this manual stack management.
That's the perfect term for it. You have to explicitly bundle up all the state needed to continue the task, like which client socket needs the data, what part of the file was requested, etc., into some kind of data structure, often called a continuation or callback object. You store this somewhere, maybe associating it with the asynchronous request. When the completion event arrives, you retrieve the save state object so the completion handler knows what to do next. It fundamentally changes the programming style. Instead of linear code flow within a function, you often end up breaking down logical operations into a series of smaller, separate event handlers or callback functions, explicitly passing state between them. This can make the code, especially for complex multi-step operations, much harder to write, read, debug, and maintain compared to the straightforward sequential logic within a thread.
That sounds complicated. And what about multi-core systems? Does the event-based approach still give you that lock-free advantage if you want to use multiple CPUs?
Not really, no. To actually utilize multiple CPU cores effectively with an event-based architecture, you usually have to run multiple independent event loops, perhaps one per core, or somehow allow multiple event handlers to run in parallel on different cores. As soon as you have multiple handlers potentially executing concurrently, you're right back to the original problem. Multiple things might try to access the same shared data structures at the same time, so you need to reintroduce locks or other synchronization mechanisms between these parallel event loops or handlers, losing much of that single-threaded simplicity benefit.
Okay, so the lock-free part is mainly a single-core advantage. Any other downsides mentioned for the event model?
A few others come up. Integrating with existing libraries or system calls that might unexpectedly block, even briefly, like a page fault inside the kernel when accessing memory that needs to be swapped in from disk, can still potentially stall the single event loop and hurt responsiveness. The sources also highlight code brittleness. If an API that an event handler relies on suddenly changes its behavior from being reliably non-blocking to potentially blocking, maybe in a library update, you can't just keep using it. You have to fundamentally restructure that handler, often, as the source puts it, ripping itself into two pieces to accommodate the new asynchronous or blocking nature. It requires significant refactoring.
So pulling it together on event-based concurrency is a totally valid alternative to threads, often great for I/O-bound servers, but it comes with its own very different set of significant trade-offs and challenges, especially around handling any blocking operations and managing the state across asynchronous calls.
Absolutely. It offers potentially simpler synchronization on one core and fine-grained control over scheduling, but you trade that for complexity in dealing with blocking I/O and managing state explicitly, manual stack management. Neither threads nor event loops are universally better. They're different tools suited for different kinds of problems, each with its own pros and cons that you need to weigh based on your application's needs.
Wow, okay. We have really covered a lot of ground here. We started with the basics of threads, why we use them, how they differ from processes. Then we hit the core problem, race conditions, and the need for mutual exclusion. From there, we dove deep into the main synchronization primitives.
Right, locks for enforcing that mutual exclusion around critical sections. Condition variables for allowing threads to wait efficiently for specific conditions to become true, hand in hand with locks. And semaphores, the more general primitive, useful for locking, signaling, and managing resource counts, but also needing careful use with mutexes.
And we explored the pitfalls, like returning stack pointers, forgetting initialization, the dangers of if instead of while for condition waits, the necessity of hardware atomics, the inefficiency of pure spinning, and the importance of OS support for sleeping locks. Then we contrasted that whole world with the event-based approach, its reliance on non-blocking I/O, its lock-free advantage on single cores, but also its major hurdles with blocking calls and state management.
It really boils down to two fundamental problems concurrency introduces. First, protecting shared resources from simultaneous access, the mutual exclusion problem solved by locks. And second, coordinating the execution of different threads when one needs to wait for another to do something or for some condition to be met. The signaling ordering problem solved by condition variables or semaphores.
Now, what were some of the key design principles or best practices that the sources really seem to hammer home throughout all this?
Several recurring themes came up. Keep your synchronization code as simple and localized as possible. Complexity breeds bugs here. Minimize the amount of interaction needed between threads. Less sharing often means fewer synchronization headaches. Always, always, always initialize your locks and condition variables before using them. And check return codes from synchronization calls. Be incredibly careful when passing arguments to threads or returning values from them, especially avoiding pointers to memory on a thread stack. Remember, each thread has its own private stack that vanishes when it exits. Don't try to build your own signaling mechanisms using simple shared flags and loops. Use the proper tools like condition variables or semaphores. They handle the atomicity and waiting correctly. And maybe the most repeated practical advice: always use a while loop, not just an if, when checking the condition after waking up from a thread con wait. This handles mesa semantics, state changes after signaling, and spurious wake-ups. And maybe the most repeated practical advice: sometimes the sources also suggest a straightforward, maybe slightly less clever synchronization approach is better than a highly complex, optimized one if it's easier to reason about and verify its correctness. Big and dumb is better sometimes.
It really seems the difficulty isn't so much in learning the handful of API calls like thread mutex lock or thread conwait. Those are relatively few. The real challenge lies in the tricky logic of designing the concurrent interactions correctly and being able to reason about all the possible ways the OS scheduler could interleave the execution of your different threads.
Precisely. That's the crux of it. Designing correct concurrent programs is fundamentally hard because you have to anticipate and handle states and transitions that you don't directly control. They depend on the scheduler's whims. Thinking like that malicious scheduler the sources mention, actively trying to find the worst possible timing, the most problematic interleaving that could break your logic, is almost essential for fleshing out subtle concurrency bugs during design and testing.
So for someone listening who wants to truly get comfortable with this, to really master these concepts, what's the path forward based on the material we looked at?
Practice, practice, practice. The sources really emphasize this. They mention things like homework problems, simulation exercises, things like using specialized tools to actually visualize race conditions happening, or sitting down and implementing some of these classic synchronization problems like producer-consumer, readers-writers, dining philosophers from scratch using locks and condition variables or semaphores. That hands-on experience is invaluable. You have to build the intuition by actually building concurrent code, seeing how these primitives behave in practice, and unfortunately probably debugging the subtle bugs that arise when you miss a detail, like forgetting a lock or using if instead of while.
Yeah, practice definitely seems key, especially for finding those bugs that only show up one time in a million under specific timing conditions.
Exactly. Those are the worst.
Well, this deep dive has certainly taken us through the essential mechanisms for managing concurrent execution, drawing directly from the source materials you provided. We've gone from creating basic threads, confronting the menace of race conditions, learning how to wield locks, condition variables, and semaphores to try and bring some order to that potential chaos, and even contrasted it all with the completely different philosophy of event-based concurrency.
It's definitely a landscape where careful design, rigorous thinking, and a deep understanding of these fundamental tools are absolutely paramount. Hopefully, this discussion, guided by your sources, has provided you with a clearer map and highlighted the key insights you need to navigate this challenging but incredibly important area of computer science. Remember to check out InfoSecTube for more content like this.
Absolutely.
Yeah.
And remember, the journey doesn't really end here. Revisiting the sources, maybe trying out some of those practice problems or coding exercises mentioned, that's really how you solidify this knowledge. This topic definitely rewards careful thought and experimentation. And while you're experimenting, maybe like and subscribe to InfoSecTube. Helps us out.
It really does. The ability to correctly harness concurrency is incredibly powerful. It's what makes modern software responsive and fast. But it absolutely comes with the responsibility of needing rigorous, thoughtful design using the primitives we've talked about today.
Thanks again for joining us for this deep dive into the fascinating and sometimes frustrating world of concurrency and synchronization. We hope you found it useful. Make sure to hit that subscribe button on InfoSecTube.